Welcome to my 44th tutoring session in A-level chemistry. This is a concluding video and the second part of the two-part series on the topic van der Waals forces. Please take a moment to watch my previous video on the same topic where I explained the principles involved in van der Waals forces and the different types of van der Waals forces. This video will provide you with a better understanding of this video content. Link to the video is given in the description below. Please do watch the video. In this video, I'll explain the effect of van der Waals forces on hydrocarbons, diatomic nonpolar molecules, and monoatomic noble gases. My session will be focusing on the effect of van der Waals forces on the physical properties like melting point, boiling point, and solubility. Here's a simplified and condensed version of the modern periodic table of elements, and I have highlighted only those elements relevant or related to the discussion on van der Waals forces. This video will involve discussion on the effect of van der Waals forces on monoatomic noble gases, impact of van der Waals forces on diatomic nonpolar molecules, which includes diatomic halogens like fluorine, chlorine, bromine, and iodine, and diatomic gases like hydrogen, nitrogen, and oxygen. The video also explains the influence of van der Waals forces on the physical properties of hydrocarbons, including both aliphatic as well as aromatic hydrocarbons. Let me begin my session with a brief overview on the cycle of van der Waals forces. The first step, you will find there is fluctuation in the distribution of electrons. This is followed by formation of temporary dipoles, and later inducing dipoles in the neighboring atoms or molecules. And this results in weak attractive forces between the dipoles present in the atoms or molecules. Let me explain the concept of the cycle of van der Waals forces with respect to the noble atomic helium gas. That is chemically stable, chemically inert, and neutral in nature. The neutral helium atom nucleus contains 2 protons with 2 negatively charged electrons in the outermost valence shell. We all know that electrons are always in constant motion, and as a result, there is a temporary or momentary fluctuation in the moment of electrons, leading to the clustering of electrons on one side of the atom. And this leads to development of dipole in the helium atom. Now, after the dipole is developed, you can see there is unsymmetrical distribution of electrons in the helium atom with a dipole. Whereas in case of neutral helium atom, you will find that there is symmetrical distribution of electrons. Now we have a helium atom with dipole. And when this helium atom with a dipole, when it approaches another helium atom, or when another helium atom approaches this helium atom with a dipole, there is enormous amount of repulsion between the negatively charged electrons present in the outermost valence shell. And as a result of this repulsion between the negatively charged electrons present in the outermost shell, a dipole is induced in the another neighboring helium atom. Now we have a dipole in helium atom B and a dipole in helium atom A. So end result is a weak attractive force between helium atom A and B with dipoles. And that is how a weak attractive force exists between neutral monoatomic noble gas like helium. So it's all about development of dipoles and interaction between these two dipoles in corresponding atoms or molecules, leading to weak attractive force. Now noble gases are present in the last group in the periodic table of elements. They are monoatomic in nature. And as you go down the last group of the periodic table, that is in the monoatomic noble gases, you will find the size of the atom increases. Because as you go down the group, the number of shells increase. With the increase in number of shells, there is increase in the atomic size. And as the number of shells increase, the number of electrons increase. And with the increase in the number of electrons, the electron clouds become more polarized. Or you can say the tendency to the polarizability is more. And as an outcome, the van der Waals force between the atom increases. That is between the monoatomic noble gases. And this leads to increase in the physical properties of monoatomic noble gases like melting point and boiling points. So what is depicted in this table is a list of noble gases with their corresponding atomic weight. So you can see as the size of the noble gas increases, there is corresponding change in the physical properties of the noble gases like melting point and boiling point. So this is because of the increase in the intermolecular van der Waals forces between the atoms. Now moving on to the halogens. Now halogens are non-polar molecules, and halogens do not exist in the elemental form, rather they exist in the molecular form. They exist as diatomic halogens, diatomic molecules. Now, halogens belong to the 7th group in the periodic table, and as you go down the 7th group, you will find the size of the atom increases. So there is increase in the size of halogens down the group, because as you go down the group, the number of shells increase. So with the increase in the number of shells, there is corresponding increase in the number of electrons. And as a result of increase in the number of electrons, the electron cloud increases, and there is tendency for the electron clouds to be more polarized. Or you can say the polarizability of the atom increases as you go down the group. And the end result is that the intermolecular force, that is the van der Waals forces between the molecules, become stronger, resulting in greater attraction as you move down the halogen group. And this strong intermolecular forces as you go down the group is reflected in the physical properties of the halogens as you go down the group. So the size of the atom increases. Here the size is mentioned in picometers. So with the increase in the size, you can see there is drastic change in the physical state of the halogens. So fluorine and chlorine exist in the gaseous state. Bromine exists in the liquid state, while the iodine exists as a solid. So iodine exists as a solid at room temperature because of stronger intermolecular forces between the iodine molecules because of its bulkier nature or of its bigger size. So as the size increases, the electron clouds tend to be more polarized, and as a result of polarizability, there is dipole induced easily, and this leads to strong van der Waals forces existing between the iodine molecules. So this stronger attractive force between the iodine molecules that leads to the solid state of iodine at room temperature. So iodine is a non-polar molecule, and the electrons are equally shared. There is a bonding pair of electrons are equally shared between both the iodine atoms. But there is a momentary or temporary fluctuation of electrons and leading to dipole. A temporary dipole is formed, and this induces a dipole in the neighboring iodine molecule, and there is weak attraction between the two iodine molecules with dipoles. That is the intermolecular force or the van der Waals force. Now moving on to the aliphatic hydrocarbons. In case of aliphatic hydrocarbons, like for example in case of pentane, the carbon atoms, they live at the ends and bends of the aliphatic chain of pentane, and the same mechanism or principle holds good even in case of aliphatic hydrocarbons. Dipole is formed, and the dipoles between the two chains of the alkane leads to van der Waals attraction, and with the increase in the length of the chain, the number of intermolecular forces increases, or you can say the number of attractive forces increases with the length of the carbon chain. So this is clearly reflected in the boiling points of these three alkanes, that is pentane, hexane and heptane. You can see with the increase in the length of the carbon chain, there is corresponding increase in the boiling points. So pentane it is 36, hexane it is 69, and heptane it is 98 degrees Celsius. So there is drastic increase in the boiling point with the increase in the length of the carbon chain. So as the number of carbon atoms increase, the number of electrons increases, and with the increase in number of electrons, the possibility of induced dipole-dipole forces increases. This leads to strong intermolecular forces as the aliphatic chain is more flexible, leading to more contact points and increased surface area. And the end result is there is a corresponding increase in the boiling point. Now what is depicted in this table is the change in the physical properties of alkanes with the increase in the length of the carbon chain. So you can see the change in the physical state. So you not only see the change in the physical state of alkanes after a particular point, also a change in the melting and boiling points. So methane, ethane, propane and butane, they are gas at room temperature, while pentane, hexane and heptane are liquid in nature. So as the carbon chain increases, the number of intermolecular forces also increase. And as a result of increase in the number of intermolecular forces, there is stronger attractive forces existing between the two aliphatic chains. And because of the increase in the strong attractive intermolecular forces, there is change in the physical state. From the gas to the liquid phase. And this is one of the possible mechanisms for the interaction between the two aliphatic chains or aliphatic hydrocarbons. So you see a change in the physical state, that is from the gaseous state to liquid state. At the same time, you also see change in the melting and boiling point. As the carbon chain increases, there is a corresponding increase in the melting point as well as the boiling point, with increase in the number of strong attractive intermolecular van der Waals forces. Now talking about the aromatic hydrocarbons. So let me begin with benzene. Now benzene is a six-membered aromatic compound. It is a cyclic and planar compound. And each carbon in the six-membered aromatic ring is sp2 hybridized. And each corner of the benzene ring represents one carbon atom covalently bonded to hydrogen atom. The carbon atoms are covalently bonded to each other in a cyclic manner, and they exist in a particular plane, or I can say they exist in one particular plane. Now each carbon atom in the benzene ring, it has a p orbital, and the p orbital, it contains one odd electron. Now these p orbitals present in the carbon atom, they are perpendicular to the plane of the ring, that is the sigma bonds linking the carbon atoms. Now these p orbitals, they are parallel to each other. As a result, they tend to overlap. Now, because of the continuous overlapping of this parallel p orbitals, it leads to formation of, or it results in a formation of delocalized pi molecular orbital. You see a electron cloud above the plane of the ring and electron cloud below the plane of the ring. So electron density is more above and below the plane of the ring. And these are the two possible resonance structures of benzene, the Kekulé structure. But the actual structure is the resonance hybrid. Now resonance hybrid is the actual structure of the benzene ring. So there is resonance whenever a molecule can be represented by two or more structures, and these structures differ only in the arrangement of electrons. So there is resonance only when a molecule can be represented by two or more structures that have the same arrangement of atoms but differ in the arrangement of electrons. So this is rightly applicable to the benzene ring. where there is change in the movement of electrons, but the position of the atoms remain one and the same. So there is no alteration in the atoms, the position of the atoms, but there is alteration in the or change in the movement or location of electrons. And this leads to delocalization and resonance stabilization. So this delocalized pi molecular orbital, it's represented in the form of a ring. What you see at the center of the ring. So the ring, what is seen at the center, is a symbolic representation of delocalized pi molecular orbital. Now we'll be considering three different examples of aromatic compounds, that is benzene, naphthalene, anthracene. Now van der Waals forces hold these aromatic rings together, be it naphthalene, benzene or anthracene. So what holds these aromatic compounds? It is the van der Waals forces. So it is the van der Waals forces between the benzene molecules, van der Waals forces between the naphthalene molecules, and the van der Waals force between the anthracene molecules that holds the molecules together. And with the increase in the number of rings, the number of intermolecular forces, they get stronger, and that is reflected in the melting point of benzene, naphthalene, and anthracene. So in case of benzene, melting point is 6, in case of naphthalene it is 80, and in case of anthracene it is 217. So with the increase in the number of rings, there is corresponding increase in the intermolecular forces. The intermolecular force gets stronger as the number of rings increase. And with the increase in the number of strong intermolecular force between the rings, you can see there is a corresponding increase in the melting point. So it is the van der Waals forces that holds these aromatic rings, that is a planar aromatic rings, be it benzene, naphthalene or anthracene together. So there is increase in the melting point with the increase in the van der Waals forces. So there is increase in the van der Waals forces with increase in the number of rings. When I say there is increase in the number of rings, I am also referring to the pi electrons. So there is increase in van der Waals forces with increase in number of rings and pi electrons. And same holds good even for the aliphatic hydrocarbons like pentane, hexane and heptane. So there is increase in the boiling point of the open chain aliphatic hydrocarbons, that is pentane, hexane and heptane, with increase in number of atoms and sigma electrons. So there is active involvement of pi electrons in case of aromatic rings and involvement of sigma electrons in case of aliphatic alkanes. So in case of aromatic system, the increased melting point is due to higher van der Waals forces as the number of rings and pi electrons, that is the electron cloud, increases. And in case of aliphatic system, there is increased boiling point due to higher van der Waals forces as the number of atoms and sigma electrons increases. So as the carbon chain increases in case of aliphatic system, the number of intermolecular forces gets stronger. And in case of aromatic system like benzene, naphthalene, anthracene, which is clearly depicted in this table, so as the number of rings increase, you not only see a change in the physical state, but also you see a drastic change in their melting and boiling points. So benzene is liquid at room temperature, while naphthalene and anthracene are solids at room temperature. This is because of increase in the number of van der Waals forces or the intermolecular forces. Now in the aromatic ring, now each corner represents a carbon atom covalently bonded to a hydrogen atom. Now, definitely there is a difference in the electronegativity between the carbon atom and the hydrogen atom. Though the difference is not too much, but there is a difference. A carbon with the electronegativity of 2.5 on the Pauling scale, and hydrogen has a electronegativity value of 2.1. So there is a difference of 0.4 on the Pauling scale. So as a result of this, there is temporary or momentary fluctuation of electrons towards the carbon atom. Now we will find aromatic pi-pi stacking interactions in case of benzene, naphthalene, anthracene. So aromatic pi-pi stacking interactions are non-covalent forces that exist, and these are the forces that hold the molecules together, be it benzene, naphthalene or anthracene. So the rings can stack in three different ways. The rings can stack in a sandwich pattern, or in a displaced arrangement or displaced alignment pattern. And there are two other possible interactions between the aromatic rings. It could be T-shaped orientation or Y-shaped orientation. So as I already mentioned, so it is the van der Waals forces that hold the benzene and naphthalene molecules together. And it requires very minimal energy to separate benzene or naphthalene molecule from one another. Now the ring what you see at the center is a symbolic representation of the delocalized pi molecular orbital, representing the pi electron cloud above and below the plane of the ring. And therefore the density of the negative charge or the electrons is much greater at the center of the ring, rather at the terminal ends. So the terminal ends of the aromatic rings, you will find the hydrogen atom with a partial positive charge because of their low electronegativity values. So it is a combination of dispersion and induced dipole interactions that holds the aromatic rings together. So this is equally applicable in case of naphthalene ring, benzene as well as anthracene rings. And it is this dipole induced in each aromatic ring that interacts with each other. And when you try to dissolve naphthalene, solid naphthalene in liquid benzene, so very minimal amount of energy is required to separate the naphthalene molecules. So there is swapping of van der Waals forces. So when you add the solid naphthalene to liquid benzene and stir for a while, you can see that the solid naphthalene disappears completely because there is swapping of van der Waals forces. The position of the benzene molecule is taken by a naphthalene molecule. And it takes very minimal amount of energy to separate one naphthalene molecule from another. Now the aromatic pi-pi stacking interactions are non-covalent forces, and the interactions are a combination of dispersion and dipole-induced dipole interactions. And the rings can stack in four different ways. They can stack in a sandwiched or displaced arrangement. Now the major drawback in case of sandwich type of interaction is that there is face-to-face interaction of the electron clouds, and as the electron clouds are negatively charged, they tend to repel each other. So in case of eclipsed or sandwich type pi-pi stacking interactions in benzene dimer, there is unfavorable type of interaction. And the only positive interaction that you can find in case of the sandwich type of interaction is the interaction between the hydrogen atom with positive charge, partial positive charge, and the pi electron cloud at the center, where the electron density is more. And second type is the displaced type pi-pi stacking interaction in the benzene dimer. And here you find a favorable and a stable type of interaction because the rings are slightly displaced away from their positions. And you can see a offset, slight displacement of the aromatic rings, resulting in favorable interactions. And third type is the T-shape interactions in benzene. And this is also a favorable type and a stable type of interaction. And they say a perpendicular interaction between the two benzene rings. And the last type of interaction is the Y-shaped orientation. And in case of Y-shaped stacking interactions in the benzene dimer, you will find a favorable interaction and a stable type of interaction. Now the solubility of nonpolar aromatic naphthalene molecules in nonpolar liquid benzene is due to van der Waals force or van der Waals interaction. And same holds good even for aliphatic compounds like pentane, hexane and heptane. So in case of aliphatic system, it is the interaction between the sigma electrons that leads to corresponding increase in the boiling point. While in case of the aromatic system, it's because of the stacking of this aromatic rings, or I can say aromatic pi-pi stacking interactions. So the interaction or the intermolecular force is a combination of dispersion as well as induced dipole-dipole interactions. So nonpolar naphthalene molecules dissolve in nonpolar benzene solvent due to van der Waals interaction. So it is a result of the van der Waals force or interaction between the benzene molecules with the dipole interacting with the dipoles of the naphthalene rings. So you can see the swapping of the intermolecular van der Waals forces between the benzene and the naphthalene molecules. So intermolecular force between the benzene molecules is swapped or replaced by the naphthalene molecules. And it takes very minimal amount of energy to separate one naphthalene molecule from another. And similarly, less amount of energy is required to separate one benzene molecule from another. And in case of aliphatic hydrocarbons like pentane, so when you try and dissolve pentane in hexane, which is also liquid in nature at room temperature, so both can be intimately mixed, resulting in a clear solution. So when you mix pentane in hexane and stir, well, they dissolve, giving a clear solution. And this again because of van der Waals force or van der Waals interaction. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.